What is time? It's a question humans have pondered for millennia. We see its effects etched across the cosmos. The sun blazes its daily trail across the sky. Seasons cycle, bringing change to our world. We are born, we live, we age. It feels like an unstoppable river always flowing, a universal rhythm, a constant companion on our journey. But is our everyday experience of time the whole story? Is time truly this unyielding universal metronome? Does it tick at the same rate for everyone, everywhere? Imagine you're on a distant galaxy moving at incredible speed. Would your watch still agree with one back on Earth? For a long time we believed time was absolute, a steadfast backdrop against which all events unfolded. The great Sir Isaac Newton envisioned it this way. He saw time as a single cosmic clock. Its ticks were the same throughout the universe. Then, at the dawn of the 20th century, a new vision emerged. Albert Einstein proposed that time was not separate from space. Instead, they were woven together, a single fabric called space-time. Einstein's ideas about time began with his special theory of relativity. Published in 1905, his miracle year. This theory rests on two fundamental postulates. The first is that the laws of physics are the same for everyone. For all observers in uniform motion, not accelerating. No matter how fast you're going, physics works the same. The second postulate was truly revolutionary. It concerns the speed of light in a vacuum. Einstein declared that this speed is constant. It's the same for all observers, regardless of their motion, or the motion of the light source itself. This constancy of light speed has profound consequences. If speed is distance divided by time, and the speed of light is constant for everyone, then distance and time themselves must be relative. They must change depending on the observer's motion. Space and time were no longer absolute and independent. They became intertwined, forming a four-dimensional continuum space-time. Imagine space-time as a vast, flexible cosmic fabric. Our motion through space affects our journey through time. This interconnectedness is the heart of relativity. One of the most startling outcomes of special relativity is time dilation. It means that time passes differently for different observers. Specifically, the faster you move through space, the slower your clock ticks relative to a stationary observer. Time itself is actually passing more slowly for you. This isn't science fiction, it's a fundamental aspect of our universe. Imagine twins, one stays on Earth, the other boards a spaceship, rocketing off near light speed. She travels for what seems like a few years to her. Then she turns around and returns to Earth. When she lands, she finds her twin is much, much older. Decades might have passed for the Earthbound twin, while only a few years went by for the space traveler. This is the famous twin paradox, a thought experiment illustrating time dilation. Why does this happen? Because of that constant speed of light. Everyone must measure light moving at the same speed, CE. If you're moving very fast, your measurements of distance and time must adjust to keep c constant. Your personal experience of time remains normal, but an observer watching you would see your clock and your life progressing slower. As you approach the speed of light, the effect becomes dramatic. Let's bring this down to Earth, or rather, just above it. Consider the astronauts aboard the International Space Station, ISS. They are our planet's fastest human travelers. The ISS orbits Earth at about 28,000 kilometers per hour. This incredible speed, while far from light speed, is significant. It means astronauts on the ISS experience time dilation. Their time passes just a tiny bit slower than ours on the ground. For every 6 months an astronaut spends on the ISS, they age about 0.005 seconds less than people on Earth. You wouldn't notice it in your daily life, but it's a real measurable effect. It's a direct confirmation of Einstein's theories. Our astronauts are living, breathing proof of time dilation. We have incredibly precise atomic clocks. These clocks can measure these tiny time differences, and they confirm that time indeed runs slower for the astronauts. So when they return to Earth, they are slightly younger than they would have been if they had stayed put. This effect is primarily due to their speed special relativistic time dilation. There's another factor at play related to gravity which we'll explore, but for the ISS astronauts the speed effect is dominant. They are moving fast, so their clocks tick slower. Section 5. Gravity's gentle bend. How mass shapes the flow of time. Einstein didn't stop with special relativity. He realized it didn't account for gravity. So he spent another decade developing his general theory of relativity. Published in 1915, it presented a new picture of gravity. Newton saw gravity as a force pulling objects together. Einstein saw it differently, more profoundly. He described gravity as a curvature, a warping of space-time, caused by the presence of mass and energy. Imagine space-time as a trampoline. Place a bowling ball in the center, that's like a massive star. The fabric of the trampoline curves, it sags under the weight. Now roll a marble nearby, that's like a planet. It doesn't get pulled by the bowling ball directly. Instead, it follows the curve in the fabric created by the bowling ball. This is Einstein's vision of gravity. Mass tells space-time how to curve, and space-time tells mass how to move. If gravity warps space-time, it warps both space and time. General relativity predicts that time runs slower in stronger gravitational fields. The more massive an object, the more it curves space-time, and the slower time passes nearby. Section 6. Worlds apart. Time's pace from Earth to black holes. Let's consider the effects of gravitational time dilation. Here on Earth, the effect is very subtle. Our planet's mass creates a gentle curve in space-time. Time passes slightly slower at sea level than on a mountaintop. Why? Because sea level is closer to Earth's center of mass. The gravitational field is marginally stronger there. The difference is incredibly small, nanoseconds per year. But with atomic clocks, we can measure it. Now let's journey to a place of extreme gravity. A black hole. A black hole is what's left when a very massive star collapses. Its gravity is so immense that nothing, not even light, can escape. It warps space-time to an incredible degree. As you approach a black hole, the gravitational pull intensifies dramatically. And so does the effect on time. Time near a black hole would slow down tremendously. Imagine you're in a spaceship, safely observing a friend. Your friend bravely ventures close to the event horizon of a black hole. As your friend gets closer, you would see their clock ticking slower. Section 7. Time detectives. Catching relativity in the act. Einstein's theories of relativity were revolutionary, but science demands evidence, experimental proof. How could we test these strange ideas about time? One of the earliest confirmations came from observing starlight. During a solar eclipse in 1919, astronomers saw light from distant stars bending as it passed near the sun. This confirmed general relativity's prediction that gravity bends light. Because gravity warps space-time and light follows those curves. But what about time dilation itself, the direct slowing of time? One famous experiment was conducted in 1971. It's called the Haffel-Keating experiment. Physicists Joseph Haffel and Richard Keating flew atomic clocks. These are incredibly precise timekeeping devices. They flew them on commercial airplanes circumnavigating the globe. Some clocks flew eastward, some westward. When the planes landed, the clocks were compared to reference clocks that stayed on the ground at the U.S. Naval Observatory. The results were astounding, yet perfectly predicted. The clocks that flew eastward, moving with Earth's rotation, lost a tiny amount of time, ran slower. This was due to their higher speed relative to Earth's center. Section 8. Navigating by starlight and space-time GPS and everyday relativity. You might think time dilation is just an exotic concept, something relevant only for physicists or astronauts, but its effects are woven into our daily lives, in ways you might not even realize. Consider the Global Positioning System, or GPS. Many of us use it every day for navigation. That little device in your car or phone relies on Einstein's theories of relativity to work accurately. The GPS network consists of dozens of satellites, orbiting Earth at an altitude of about 20,000 kilometers. These satellites carry extremely precise atomic clocks. They continuously transmit signals with their time and position. Your GPS receiver on the ground picks up these signals. By comparing signals from at least 4 satellites, it can calculate your exact location on Earth. But there's a relativistic catch. The clocks on GPS satellites are affected by both types of time dilation. First, they are moving fast, about 14,000 kilometers per hour. This speed causes their clocks to run slower than ground clocks, by about 7 microseconds, millionths of a second per day. This is special relativistic time dilation. Second, they are at a high altitude where Earth's gravity is weaker. Section 9. Our cosmic clock time dilation and the universe's story. Time dilation isn't just a curious quirk of the universe, it's a fundamental feature that shapes our understanding. It tells us that time is not a rigid universal constant. Instead, it's a dynamic, malleable component of space-time. Its flow depends on your motion and your gravitational environment. This realization has profound implications for how we see the cosmos and our place within it. It opens up new ways of thinking about past, present, and future. Consider the vastness of the universe. Light from distant galaxies takes billions of years to reach us. When we look at these galaxies, we are looking back in time. The principles of relativity help us interpret these cosmic signals. They help us understand the expansion of the universe, the behavior of objects near extreme gravitational sources, like neutron stars and supermassive black holes at galactic centers. Time dilation is a key ingredient in our cosmological models. What about the future of space travel? If we could build spacecraft that travel near the speed of light, time dilation would become incredibly significant. Astronauts could journey to distant stars in what feels like a short time for them, while centuries or millennia pass on Earth. This prospect raises fascinating possibilities and ethical questions.